So before the break, we got to the point where we had a formal definition of a finite element in terms of the shape of the thing you were going to put it on, which polynomials you wanted to be able to represent, and the nodes, by which we meant how you wanted to specify, in some sense, where the solutions lived. So that is a really abstract concept, particularly since it's defined in terms of the dual functions to the finite element space, and that's a concept which probably most of you were familiar with for about 10 minutes before we used it in anger. So let's do the simplest case we can think of. So let's do, so this is going to be, that's K, right? That's the domain, which we can verify is closed and bounded, non-empty interior, subspace of R1 in this case, right? So this is the dumbest case we can think of. And what we now want is we need a polynomial space. So the polynomial space we're going to choose is the space of all linear polynomials. And so you actually get into a catch-22 here, right? Because how do I write down the linear polynomials? Well, actually, the only way to write down functions in a function space algebraically is with respect to some basis. That's always true. There is no other way of doing it. However, there is a sort of universally conventional basis that we think we understand. And so what we're sort of interested in is how do we write down basis functions so on compared to that. So the universal basis that we think we understand is the basis for one-dimensional polynomials, which is 1x, x squared, x cubed, and so on. Right? That's the basis with respect to which you normally write down a polynomial. You write down some coefficient times this one plus some coefficient times that one and so on. That's the normal way of writing down a polynomial. And since we're only interested in linear polynomials, we can do that. And in fact, you could just stop there, right? You could run your whole life just by saying, okay, I've already got a basis, so life's good. That's perfectly good basis for these ones. So that's the function 1, that's one of my basis functions, and the function x, that's another one of my basis functions. And it turns out that using those two functions, I can in fact write down all of the linear functions on the line. Yeah.
Would this work for triangles? For 2D?
So in 2D, the basis that you have is 1
x squared,
x squared, y squared, xy, xy squared, x squared, y, and so on out there. Right? That's all the polynomials are go out that way.
Well, why do we need to enumerate x squared y when we can form it from x squared and y?
You can't.
Can't we just multiply them?
No. You can only add basis functions together. You can't multiply them. Right? The only operations you have in a vector space are addition and multiplication by a scalar. Vector multiplication is just not part of the game. So we could do this, however, and in fact, it's not quite as dumb as it sounds. Like there are bases that look not radically dissimilar to that out there for various spaces. But it doesn't enable us to choose our nodes, and it will turn out to be the case, particularly for getting the continuity right, that being able to choose the nodes is a really important part of this. So what we want to do, so we already understood previously that there's an infinite set of bases, right? There are lots and lots of different bases I could use even for this very simple function space. And so what I'm now interested in doing is picking my set, and the set I'm going to pick are the most common ones, the ones that are almost universally used for this element, and those are point evaluation here and point evaluation here. Right, so n 1 of phi equals phi 0, n2, subscript 2 of phi is equal to phi at 1. So these nodes are in the dual space. They are things which take a function and give me a number. Now what I want to know is, what are the basis functions that go with this? And now you can probably intuitively reason out what they ought to be, but actually we can mathematically derive what they are. And they fall out quite nicely. And so the mathematical derivation is that these nodes give me a set of functions to solve. So I know that I'm going to be solving for two basis functions. Right? I know this from a bunch of ways. I know it partly because that was true over here already, right? And the number of basis functions is invariant. It's also universally true that the number of basis functions for the primal space, the original space, is equal to the number of basis functions required for the dual space. That's one of the properties of the dual space and the primal space looking a lot like each other. And so I know I have two functions which are like that, which are in the space P1. So by P1 we mean the linear polynomials. 1. P1. And so now I can feed all of these functions to each of these, right? So I know, so what am I going to be doing here? I'm going to be working out what these functions are. Well, we previously pointed out that the only sense in which you can say what functions are is you can say what they look like compared to some other basis, right? The only operation in town is changing basis. So we're going to do it with respect to this basis. So that means I get alpha 1, so phi 1 is equal to alpha 1 plus beta 1 times x, and phi 2 is going to be equal to alpha 2 plus beta 2 times x. So that's all I'm saying is somehow I can represent these functions as some coefficients times this basis. So now I can take one of these, so let's take phi 1 for starters. And I can substitute phi 1 in here. Now remember, what do I know? If this is the basis dual to this, what I know is that when these basis functions hit these basis functions, then I have to get out the delta function. So I have to get the Kronecker delta. So that means that n1 of phi 1, which is equal to alpha 1 plus beta 1 times 0 times x at 0, because that's what this node means. That has to be equal to, so in this case they match phi 1 and n1, that has to be equal to 1. And now I can take n2 of phi 1, and so that is equal to alpha 1 plus beta 1 times x at 1, which is 1. And that has to be equal to 0. And so now I'm really happy. I have two equations, two unknowns. So I can solve out for what alpha and beta have to be. So in this case, I know immediately that alpha 1, sorry, I don't want the equal sign there, has to be 1, because that's 0. So alpha, that's just what the first equation says. And so then I substitute here and I find that 1 plus beta 1 is equal to 0. So I take 1 off each side. So I find that beta 1 is equal to minus 1. And I substitute back in and I find that phi 1 is equal to 1 minus x. And now I can do exactly the same thing on the other side. So let's wind back to here and do exactly the same operation, only now, instead of hitting each of these with phi 1, we're going to hit each of these with phi 2. And so now what we find is that alpha 1 plus beta at 0 has to be equal to 0 because these two don't match. And this is alpha 2 plus beta 2. I'm solving for the 2's now. Alpha 2 plus beta 2 at 1 equals 1. And I can pull the same trick. This is a very easy system to solve. So that's equal to 0. So that tells me that alpha 2 equals 0. And I substitute in here. So alpha 2 is 0. Beta 2 times 1. So that means beta 2 is 1. So that means that phi 2 is equal to x. So now I can sketch those basis functions on here, and I find that phi 1 is 1 minus x. So phi 1 is the function that looks like this, and phi 2 is the function that looks like that. So please put your hand up if you're surprised. Okay, so that's good news. We got back out exactly what we expected to be the basis for this very simple case. But the important point here is that this is a recipe for turning nodes into basis functions for any finite element in any number of dimensions. And so, to return to a theme earlier, this is really exactly what Fiat does. So when you specify a finite element in Fiat, you specify which shape you want it to be on, and in Fiat you just do that from the menu of shapes. So it supports intervals and triangles and so on. Choose a shape off the menu. You describe a function, set up a polynomial space with respect to a basis. It turns out they don't use this basis, and the reason they don't use this basis is actually for numerical purposes, this is a crap basis. So if you look at what happens just on the interval 0, 1, in a hand-wavy sense, so 1 looks like this, x looks like this, x squared looks like this, x cubed looks like this, x to the 4th looks like this, and so on. So as you go up through the spaces, they look more and more like each other. And so when you're looking for bases, right, the best possible bases are orthogonal. The worst possible bases are the ones that are nearly singular, and this one gets to be nearly singular for high order. So it turns out you didn't want to do that. So they chose another starting point, which is a nice orthogonal basis for the polynomials. So that's great, and you can ask yourself why you wouldn't just use that space as your finite element space, and the answer is that it's not a nodal space. It's not a space which is defined by these nodes. So there are people who do modal finite element methods. It is possible, but there are at least major simplicity advantages to doing nodal-based ones. So what you do is you take your nice basis, which they call a Dubiner basis, you write down what your nodes are, and then it automatically forms this linear algebra system, solves the linear algebra system for what the basis functions were. And that's the thing that you get back out of there. Okay, so let's move forward, and I'm going to sketch the next lemma, because the next lemma, so this will be the last bit of theory we do in here, and then we'll just look at some finite elements and explain how this pans out for triangular and quadrilateral finite elements. But we're just going to do a tiny bit of theory that we won't prove properly, but we'll state it and argue about it, and this is the theorem that says that this works. So, if P is a d-dimensional vector space, so once again, this is a statement which is true for all vector spaces, but we're really only interested in function spaces, but that's a subset, so that's cool. And N1 to ND is a subset of the dual space. So these aren't vectors, they are functionals on those vectors, linear functionals on those vectors. Sorry, yes. They are in P. Then A, if, well actually no, I don't want to write it there. So A, this statement, N1 up to ND is a basis for P prime. That is an equivalent statement to, so implies both directions, B given V in P such that, so here's a nice fun piece of notation that they use. So what they want to write is Ni of V equals 0 for all I, so for all the ones in that set. What they actually wrote was Ni, and then they left the brackets off, which is a typical mathematician's notation for this. It's just not the one they used in the rest of the book. They forgot the notation they were using. Then V must be the zero function. So what that is saying is that in some senses this nodal basis for the dual space fully determines what goes on in the polynomial space. So it says that if I had any function at all that was 0 when tested with all of the nodes, there's only one function that could possibly be, and that's the 0 function. And so that's the basis on which this works, right? If it were the case that I could have functions which weren't seen by any of these and weren't the trivial 0 function and were still in P, then I wouldn't have determined P, right? I would have bits of P that were not described by these nodes. So let's just make that kind of concrete. Let's go back to our favorite space. There's the interval. Here's my nodes. All that statement is saying is if you're in the space, so if you're a linear function, and you're 0 here, and you're 0 here, then you are the 0 function. There's no extra spaces in there if you have any variability at all. So you can just think about that in the case of a linear function. If I take a straight line and I peg it down at one end and I peg it down at another end, then it's flat. And in 3D then, the same thing applies. So if I'm in a triangle, now the typical nodes for the linear space are these three. and I peg down here, and I peg down here, and I peg down here, and all linear functions that obey that are the zero function. So that's what tells you that that your set of nodes is sufficient to completely nail down the space. As I said, we're not going to take the time to go through the proofs of that, but that's the and the terminology that's used in that circumstance is we say that n, the set of nodes, determines P, if this is true. Right? That's a fairly intuitive piece of terminology, right? What it's basically saying is that n has told you everything about P. Now, let's think about these triangular elements. It's a fun place to be. And this is an illustration now. We're going to start talking about what the possibilities are for having finite elements. So one of the things we now know is if our space is P1 in 2D, then that space is a three-dimensional space. I need three nodes. And if you want to illustrate that with respect to the basis that you already understood, all functions in here have the form a plus bx plus cy. So it means to be a linear polynomial in two dimensions. And so there are three unknowns in there. Those are three basis functions. They're not three useful basis functions. But as we've just learnt in this lecture, if I define three nodes, I can get three basis functions out. It also turns out to be the case that I have to now start caring about how I'm going to join up my functions together. So if I only want my global space to be in L2, so if I don't care at all about continuity between elements, then I can choose whatever nodes I like. If I want continuity, then I have some constraints about where my nodes are. And the constraints are that I need the nodes on each of the facets of my elements. So facet is a term we use to mean the one dimension down objects. So here, the ends of the facets, right? So in 1D, the continuity problem is fairly trivial. The reason is that the space of functions which can exist on the endpoints in one dimension is a one-dimensional space, right? The only thing that can happen here is that the function can take one value here. And so if you need continuity, in this case, then you must have a node at each end of the interval. If you don't have a node at each end of the interval, then you have not enforced continuity in the function space using the nodes, right? That was simple. What needs to happen in more dimensions? So in more dimensions, it needs to be the case that the nodes on the facet determine the polynomial space restricted to that facet. Right, so we understood what determine means now. So what does that mean in this case? So if we have two-dimensional linear objects, we need three nodes. Now if we consider that polynomial space restricted to one edge, so it's still going to be linear polynomials, and it's linear polynomials in one dimension. So linear polynomials in one dimension are a two-dimensional space. So that tells you that you needed to have 2 nodes on each edge in order to get continuity, full continuity between the elements. Right? And the reason is that the edge nodes, the facet nodes, are going to be shared across the edge, right? They're the ones that this guy also has. And so if these nodes determine all the linear functions along this edge, then that guarantees that the restriction to the edge of the functions in here has to be the same as the restriction in edge of the functions on here, because they're determined by the same set of nodes. If I don't have that restriction, then I have some more other options. So if I'm prepared to be completely discontinuous, I can take off, and I can put these anywhere I like. So I could, for example, put my nodes kind of here. I could put them so that they're equally spaced away from the edges of the triangle. If there's another fun example which turns up in some circumstances where I can still join them up. So in order to be able to join up my elements in every configuration, there's also some requirements about the symmetry of the points along the edges. Right? Because if I put a point down here and I put the next triangle on, it's not always possible to guarantee that the next triangle is not going to want the point to be here. And so there's a symmetry requirement. But if I relax continuity a little bit and keep the symmetry requirements, then I could end up by deciding to put my nodes down here. Right? That's on that element, that's still a perfectly good set of nodes. Because if I bolt down my linear function at those 3 nodes, then I've made it flat, it's 0, so I've determined the space. Life's good. And what this does is produces a funny sort of element, and this is where we're going to have some mathematics through the medium of interpretive dance by picking things up. So what you've done is at the edge, you've nailed the middles together. And that has an interesting effect because it means that you're not continuous along the edge, but the integral of the function along the edge is continuous. Because if you nail down the middle value of a linear function, you've nailed down what its integral is. So that turns out to be enough continuity to be interesting in some finite element circumstances. So that's called a Crucier-Ravier element. They come from way back in the 70s and have been used for a bunch of different things. As we go up the elements, so one of the beautiful and special things about triangles comes out if we start writing out the traditional basis in a particular way. Let's write out, so the traditional basis, I mean this basis, the basis for polynomials. So let's progressively write out the basis for higher and higher order polynomials in 2 dimensions. So let's start off with the basis for the 0-dimensional space, the degree 0 space. So that's that, right? The constant functions, the basis is the function 1. Now, in order to get the linear functions, I need to put in x and I need to put in y. In order to get the quadratic functions, I need those ones, but I also need x squared, and I need y squared, and I need the cross term. And in order to then go to the cubics, I get x cubed, I have 2 sorts of mixed term. So hopefully most people in the room are starting to recognize Pascal's triangle appearing on the board. Now if I have triangular finite elements, this is exceptionally suggestive of a pattern of nodes that I might like to choose to use on the triangle. So it is a special property of the simplices that you get out this set of nodes. So for quadratic nodes, they go out topologically here. And hey, let's have Technicolor. In the cubic case, they go now I need a point in the middle here. And am I going to be brave to have a quartic? The quartic case, they go now I need to have, and they keep going, right? So that means that if you're on simplexes and something absolutely analogous happens on tetrahedra, so tetrahedra, I've got one more variable and it builds up in the third dimension as I come out and I build the tetrahedron. Something completely analogous happens in 1D, but that's kind of boring as well. So 1D you get just by marching down one of the edges of this thing. And so what happens here then is having a basis for a complete polynomial space that works out beautifully, that has the right number of nodes, works out nicely on triangles. And that's one of the main reasons people use triangles. That was a statement about the topology of where these points go. And I notice the fact that when I walk along that edge, I get the one-dimensional case. So that means that the continuity falls out. Right? The right number of points to determine the degree n polynomials will lie on the edges. And in 3D, what you want for total continuity is that the right number of points are on the facets and on the edges going down, and that falls out. So the same thing's true. So one of these triangles is one of the facets of the Pascal's tetrahedron, and the edges are also the same. So life's great, everything falls out. What's not true is that was not a statement about the geometry of the points. So I've drawn them equispaced. If anyone who uses Phoenix, that's the only set that Phoenix currently supports. It turns out that as you go to high order, that's not a good basis. As it turns out, as you go to high order, it's a better basis if you, in a particular way, allow the points to cluster out towards the edges. So if we just look at the cubic case, so the cubic one has points here and here, and it has 2 points on each edge, and 1 point in the middle. So the 1 point in the middle, by symmetry, has to be in the middle. Without violating symmetry, I can slide these points along their part of the edges, as long as I slide them all in the same way. And it turns out that the best, the most orthogonal basis, the best behaved basis, which obeys these constraints, is not the one where the points are equally spaced. There is a better solution where the points are a bit further out towards the edges. And more generally, that comes out in higher order. In fact, the points that you get as you go out are called the Fouquet points. And there's a really cool result that will appeal to the physicists in the room, that basically the points you get are the points that charged particles would go to if they repelled each other. So if you say that they all want to go as far away from each other as possible, and you solve for that, then you end up with a set of points which turn out to be the optimal set of points for this problem. So that's triangular elements.
So in 1D it's not the Chebyshev.
So in 1D there are multiple orthogonal spaces, which may well be the Chebyshev points in 1D, right? I think that may.
Stays at
So the other space we're worried about. So is there anyone queuing outside? No, good. So we started late, so we'll go for a little bit late to finish late. The other fun space we were talking about, which is sort of simpler in some ways, is the space where our reference element is a cube, a square. And so in this case, the natural thing to do is to span the space Qn. So Qn is the outer product of Pn times Pn. And so that's expanded out to however many dimensions you're in. Right? So this is the two-dimensional one. So that means that...
That's fine.
Oh, yeah, so this is Qn in d dimensions, and this is Pn in one dimension, where there are d things in this product. So what that means is, so let's just take the simplest one. So if I chuck a node down on each corner, I get Q1, and Q1 is not quite the linears. Right, let's work this out. All the things, so the linears in one dimension are all the polynomials of form ax plus b. And if I now have cy plus d, and I multiply out all combinations, which is what the cross product is, then I get things of form ax plus b y plus cxy plus d, where those are not the same coefficients, right? So those are all the ones I get. So that was not quite the linears, because I've got that term in there. So some of the quadratics are in there, the cross terms, not the x squares, not the y squares, but the cross terms. And that's the natural result of multiplying a linear this way by a linear that way. So that's a slightly bigger space. So the upside is that you have this beautiful tensor product formulation, which can make your evaluation very efficient. Another upside is if you have a regular mesh, this is the logical way to do it. And in fact, if you have a regular mesh for the number of degrees of freedom, these are more accurate than the triangles. You can prove that. The downside then is, in some sense, you're paying an additional tax here, because that's still only going to be second order accurate. Still only going to behave like linears, but you're carrying around some extra functions. And as you go up, so then if you put in, so that's what happens if you take the quadratics times the quadratics. And what actually happens, let's put Pascal's triangle back up, is you get 1x, y, x squared, x, y squared, x cubed, x squared y, x, y squared, y cubed, and so on. These elements draw not a triangle on Pascal's triangle, but a diamond. So the triangular elements just cut off bits of the top of Pascal's triangle. What these do is they cut these things out. So the next one, all right, so in order to do that, I needed to explain that we have the x squared, y squared term in there, right? So all the mixed terms that fall out. And so I will briefly just touch on another set of elements which are quite commonly used in this space. So in order to maintain continuity at quadratic, I needed all of the nodes around the edges, right? I needed that to bolt down the outsides. But in order to get that, I didn't need this one in the middle. So if I didn't insist on that being a node, so I made my dual space a bit smaller, I could sacrifice something out of my mixed space. In particular, I can sacrifice this. And then I've got a space which is still second order accurate, has less degrees of freedom, requires less quadrature to get right because the highest order term in here is smaller. And the world is a happy place. And this works going further up.
That's very serendipitous.
It is very serendipitous, you smart ass. So yes, these are called the serendipity elements, because it's a happy coincidence that you're able to do this. And so there's a next one up. So if we went to, where's my next Technicolor color? If we went up to cubics, then you can take out all of those. And what happens is you get the diamond which goes down to here, up in 1. It's superlinear, yeah, it's superlinear to 1, and comes out and up here and back. And the same thing goes down. So eventually, so if you're paying close attention, the number of nodes on the edge goes up linearly with the degree of freedom, whereas the number of things in here is a quadratic function. It's a triangular number. So eventually, as you go up, you do have to have some interior nodes in order to have enough nodes to determine the p-space. But you never have the full set of them. So that's another very, very common and popular set. So we're going to leave it there, where we've just about covered a bunch of the scalar polynomial spaces. And what we're going to do next week is we're going to bravely attempt to actually work out what finite element means in more dimensions, and work out how we would do a finite element problem in more dimensions.